What's going on, everyone? You're back with your boy Jono for another quick math lesson. Today we're going to have a look at velocity time graphs, meaning we're looking at the speed of an object during an experiment throughout the entire thing. These are different to our displacement time graphs because instead of tracking its position, this time we're just looking for how fast is this thing moving. So when we looked at our displacement time graphs, we knew that we were looking at the position of the object throughout its entire journey. But this time, instead of looking at our position in space, we're only looking for how fast we are moving at every second or every minute. Again, the most important thing that we look at before we even get started with these velocity time graphs is that the units are incredibly important. We need to make sure if we're moving in meters per second or kilometers per hour, and we need to know if time is in seconds, minutes, or hours. Another thing that's really important is because velocity is a vector, the direction matters as well, and we're actually going to see that in the next lesson where we can have a negative velocity and what that actually means to our graph. So to start off, we're just going to look at understanding the graph. We're not actually going to do any maths in this example. We are just looking at what's happening at every second. So the first thing that we do need to look at is we need to know that we are in meters per second north, and that north is important. The other thing that really helps here is that we are looking at seconds. The entire time of this experiment is just 10 seconds in total. So at the very start, let's just talk through what's happening. From 0 seconds, we're not actually moving and we're accelerating for 2 seconds. We go from 0 meters per second to 5 meters per second. And in that time, we are moving faster in the northerly direction. From that 2-second mark up until the 8-second mark, it looks like it flattens out. In our displacement time graphs, this would mean, hey, we're having a rest here. But that's not what's happening in a velocity time graph. All this is saying is that I'm at a constant cruising speed. I'm at 5 meters per second every single where along this line. So it hasn't meant that I've stopped, it just has meant that I've stopped speeding up. So now I'm just at a constant speed for these 6 seconds. Finally, at 8 seconds, I've got a negative gradient, and this just means that I'm slowing down. At 8 seconds, I was going at 5 meters per second, and after those 2 seconds finish, I'm at 0 meters per second. So I've just slowed down. What's really important here is that I've slowed down, but I'm still going north this whole time. I have not turned around and gone backwards. So the thing that students do struggle with these velocity time graphs are the flat line and when we've got a negative gradient. We just need to know that the flat line means constant speed, not at rest. We are still moving this whole time. We're just moving at a constant speed. So what's really happening is there's no acceleration in this time. We're just moving at a constant speed, kind of like cruise control in your car, in the northerly direction. The other thing that's important is this negative gradient does not mean that we're going backwards. All it means is that we're slowing down. It's kind of like you've put the brakes on and you're still moving forward or you're still moving towards like a traffic light, but you're going less fast, so your velocity is going down. So it's really important to know that the negative gradient means decelerating, not moving backwards. So the other type of questions you're going to be asked are, hey, what's the total displacement that I had during this experiment? And what's my average velocity for the entire trip? This is actually pretty simple. If you were good at year 8 geometry, you're going to be on top of this. So let's actually look really closely at this 2-second mark to 3-second mark. For this whole flat line, I'm saying for sure, you're going at 5 meters per second. 100%, every single second, you go 5 meters. So from 2 seconds to 3 seconds, you've gone 5 meters. And then from 3 seconds to 4 seconds, you've gone another 5 meters, so 10 meters in total. So all we're doing along this flat line is adding 5 meters, 5 meters, 5 meters, until we say that we went, 5 meters for 6 seconds, we went 30 meters north. Another way to think about this is that the height of my velocity time graph was 5 meters per second, and the length was 6 seconds. If you can find the area of a rectangle, 5 times 6, or the length times width, you know that the answer was going to be 30. And that's actually the case all the time. Displacement is defined as the area underneath the curve, just using our year 8 geometry. So from 0 to 2 seconds, we've got a triangle. The base is 2 seconds and the height is 5 meters. So to find the area of a triangle, we just have to go a half times base times height, which is equal to 5 meters. So that means the displacement that I had in those first 2 seconds is equal to 5 meters. And then if I look at the triangle at the very end, it's exactly the same. Its height is 5, its base is 2, multiply that by a half, and I'm left with 5 meters. Because remember, I'm still moving north, all of this is in the northerly direction. So then if you have to find your total displacement or total distance, all I've got to do is add up the areas under the curve. I've got my 30 and 2 5s, so I've moved 40 meters north, or my total distance was just 40 meters. And again, this is just by finding the area of simple shapes and adding them together. Finally, you might be asked to find the average velocity of your whole trip. And before we even get started, I'd like you to have a guess. We can see that our top velocity was 5 meters per second. So it makes sense that our average velocity is going to be a little bit below that because we have the speed up time at the start and the slow down time at the end. So all I've got to do is use my total displacement, my 40 meters north, and divide that by the 10 seconds. This is equal to 4 meters per second north. And that's my average velocity for the whole trip. So the big takeaways for you in order to absolutely smash a test on this topic is that we need to know what all of the parts of the graph actually mean. The first one is that the flat line does not mean at rest. It means at a constant speed. Every single measurement taken along that flat line is exactly the same as the one before it. So it's just, hey, I was going at 5 meters per second at every single interval on this part of the journey. The second thing is that negative gradient, that downward slope, does not mean moving backwards. It means slowing down or decelerating, but you're still moving in that northerly direction, the same way as you were going before. So you just need to make sure that if you see that downward slope, you don't think like a displacement graph that means moving backwards. It just means slowing down in the same direction. Finally, if we ask you to find displacement, all you've got to find is the area under the curve. My big pro tip for this is just break up the area under the curve into really easy shapes. You're going to see a lot of rectangles and a lot of triangles, and if you're on top of just writing down the formula to find those, I think you're going to be all right. Thanks so much for watching this lesson, and I'll see you later.